Welcome everyone. This is the next part of the series where I'm testing different types of thermoelectric coolers, and in this episode I'm going to test the TEC12708. So this is the 8 ampere unit, so that's the maximum current, and the setup is the same, but I repeat it quickly. So the temp one here is the green wire, which goes to the back side of the heatsink, so it's indirectly measuring the hot side temperature. And then we have the white wire, which ends up in between the fins of this CPU cooler, which cools the hot side of the Peltier cooler. And sometimes I refer to this temperature as the outlet temperature. And then we have this thermometer here, which is another green wire, as you can see, and that goes here to the cold side of the Peltier cooler, and the cold side is separated or insulated from the environment by this plexiglass and adhesive foam. And I clamped this kind of thing on top of the cold side of the Peltier cooler by some rubber bands, so there is a small amount of tension in between these parts. Then the Peltier cooler is clamped by this 3D printed plastic piece on the CPU cooler. Of course, I applied some thermal grease between the two layers, so between the heatsink of the CPU cooler and the hot side of the Peltier cooler. And then there is one fan which is pushing the air towards this direction, and there is another fan in between the two metal heatsinks, so the air is flowing in that direction, and both fans are running on 12 volts at their maximum RPM, so the cooling is running on its maximum efficiency, so to say. There is a clock here just to track the time, but sometimes I repeat certain measurements, so the time will probably jump in between the clips of the video. And then this multimeter is measuring the voltage, which is applied on the Peltier cooler, and then this is measuring the current, which is running through the circuit. And this is, as I said, an 8 ampere unit. So I will follow the same strategy as I have been following in the previous two videos. So first of all, I will see what is the Imax 50% of this device. And what this means is that I go to 50% of the maximum current, which is 4 amperes in this case. So I will run 4 amperes through this circuit and see what is the cold side temperature. I expect something around -22, -23 degrees Celsius, but we will see. And after that, when I measured the temperature at at 4 amperes, then I will increase the current. So I will probably measure it at 6, 7 amperes and maybe 7.5. I will see how the temperature changes, and maybe I will do half ampere steps in between the temperatures towards the maximum current. But when I go down from 4 amperes, I will do one measurement, let's say at 3, 2 and 1 amperes. So there will be 3 steps downwards as well. So I start the fan right now, and you can see that everything is at the same temperature. So this is our initial room temperature. So I start the fan, and now everything will be a bit more noisy. And then I turn on the power supply, which should be at 0. Yeah, there is an initial jump. So what I will do is I try to set this at 4 amperes. And if you remember from the previous videos, I mentioned several times that this circuit changes its resistance, as all circuit does, when I change the temperature. So what I have to do is I have to do some adjustments on the current when I see that the temperature of the device is changing, because the resistance is also changing, and therefore it will not be let's say at 4 amperes for the first time. So I just go and turn up the power supply to a certain value, I don't know. So you can see that it decreases the current as the temperature is changing, and you see that the temperature drops rapidly on the cold side. So this is, I accept as 4 amperes. I do some very slight adjustment to the voltage, and let's leave it here for a while, maybe 4.05. So now it's 44. So I will wait until, let's say, 50, and I come back and we will see what's the equilibrium. But you can see that my initial guess was quite okay. It's minus 22.2 degrees, and you can see that the hot side temperature goes up as well. If I touch this, it's not too warm. It's okay. It's hand warm, not even hand warm. It's very, very pleasant. So let's wait for 5 to 6 minutes, so everything will settle down and reach some sort of equilibrium, and we will see what are the readings from the different instruments. So we will come back in a few minutes. So I think 5 minutes have passed, maybe 6 or 7. So we can check the values. So 4.02 amperes, so pretty much 4 amperes. 10.69 volts, minus 23.4 degrees Celsius on the cold side, but that's impressive, and slightly higher temperatures on the hot side, which means that on the heatsink side, so the other side of this contact here, it's 27.3, and the outlet temperature is 28.3, 28.5. It's fluctuating, but yeah, it's slightly below, slightly above the room temperature. So the next step, what I will do is that I go and do a 1 ampere jump. So I go up to 5 amperes, and I wait for another 5 minutes. So let's say we will come back around 58. So I wait maybe 6 minutes, and then again we just check the temperatures. So now I just go up to 5, so you can see that I'm changing the values here, slightly overshooting it, not this much, something like this. And now I will wait for 5 minutes. So another 5 minutes passed, and it seems like that the temperature is not really moving anywhere. So we can read the numbers here. So we further decrease the temperature, and now it's minus 25.4, which means that we decreased the temperature by 2 degrees Celsius by increasing the current by 1 ampere. So it's 5 volts here, 5 amperes here, sorry, 13.13 volts for the voltage, 28.5 for the hot side, and 30 for the outlet temperature. So it seems like that this thermocouple is maybe not perfectly touching the heatsink. I will check it, but yeah, it seems like that the connection is maybe not perfect, because we are further away from this heatsink, and we are reading 2 degrees Celsius or 1.5 degrees Celsius higher temperatures. And you can see that there is some fog on the top of this plexiglass, and I can also see some ice forming, but very thin layer, because this edge, the only edge of the Peltier cooler, due to the cables, is exposed, but it's fine. So after like 5-8 minutes, because I've been talking for a while, the temperature is still minus 25.4, So we accept this as the equilibrium temperature at these environmental temperature and this current. And now I think I do another 1 ampere jump, so I go up to 6 amperes instead of going to 5.5, and we see what happens. So first of all, I change the current to 6 amperes, slightly overshooting, and we can see that the temperature is increasing, so we are still a bit far away from the Joule effect, but we are there somewhere close. So now we can wait and see what happens. Or actually I was wrong maybe, because it seems like that we are at the Joule temperature. So I changed my mind and I go back to 5.5, and then we come back to 6 later, because I want to monitor the bottom of the curve properly. So now we stop at 5.5 amperes and we wait for a while and see what happens. So we will be back in 5 to 10 minutes. So after waiting some minutes, we can see that the temperature slightly increased. So instead of minus 25.4, we are at minus 25.2. So basically we are on the boundary between utilizing the Peltier cooler at its maximum performance and getting decreased performance due to the Joule effect. So now, as compared to the previous current, which was 5 amperes, it seems like that we slightly turned on the Joule effect. So if I go to 6 amperes, which I just tried before trying this step, we will get a slight increase in the temperature here, because we start to warm up the device by running a large amount of current through it. So these are my comments regarding the temperature changes, and you can see that the hot side temperature also increased a little bit. So now we are below 30 degrees here on the temperature 1, and we are above 30 degrees by 1.5 degrees Celsius. It's not too much, but let me come back to the cold side temperature. So this is minus 25 degrees Celsius. We started at plus 25 degrees Celsius, so this is 50 degrees difference. That's pretty cool that we can create 50 degrees difference as compared to the room temperature. So the chamber here, you can still see the fog there on the top of the plexiglass. I can just try to clean it. You can see. So inside the chamber, on the surface of the cold side of the Peltier, there is it is 25.2 degrees Celsius. So the surface is 50 degrees colder than the environment. That's pretty nice. So now I see that this is basically the bottom of the curve, but despite that I just go up half more amperes. So I go to 6 amperes, wait a little bit, and then we will go to the other direction. But let me increase this value down, up, sorry. Okay, so let's call this 6 amperes, and all I will do is I wait like 5 to 10 minutes. So now it's 15. So I will come back later and we will see, but we already see that the temperature is increasing here. So now we are pushing too much current through the device, so we are not using it so efficiently. So let's see what happens in a few minutes. So we waited enough, and you can see that the temperature is minus 24.4 degrees Celsius. So the temperature went up roughly 0.8 degrees Celsius from the previous temperature. And as I said, we are at 6 amperes, 15.75 volts, and warm or hot sides are 30 and 32.5 degrees Celsius. I can now feel that this side is like slightly warm, and you can see the fog or the dew on this, and also on the side of this side where we have an exposed edge of the cold side, there is a little bit of ice, but it's not so significant. I want to make a comment about the temperatures. So now what we do is we are measuring the temperature on the cold side without any load. So that's very important. So there is basically, we can like say that there is a very negligible heat transfer from the environment towards the cold side. So that's why it is very cold. But we can also say that as far as I know, it doesn't really matter if you increase the current and you get slightly lower temperature, because you can still sort of increase the cooling power. For this, to fully confirm this, you should check the data sheet of these devices, these Peltier devices, but they don't necessarily say that you have to transfer the maximum amount of heat through this Peltier device when you have the maximum or the minimum temperature or the maximum lowest temperature that you can achieve. So this should be checked, because now there is basically zero heat transfer through the two sides, so the cold and the hot side of the Peltier cooler, but you have let's say we have more than 50, nearly 60 degrees delta T, which is almost the maximum delta T of the device, because these devices are usually rated to 65-70 degrees Celsius delta T, so this is pretty close to that value, but there is no heat transfer. So of course, if you put some thermal load on it, which I will do later, then there will be sort of a heat flux between the two sides, and this temperature will significantly increase, but you can still cool with it. So a lot of cooling power is still involved in the processes. So I reached the bottom of the curve that I want to create later on for the comparison. So now I will go down to 3 amperes, and I will check what are the values. So now I decrease the voltage, which will bring down the current, and as you can see that now I stopped, the temperature is increasing, and together with that the current is increasing, because as I mentioned previously, this is a semiconductor which behaves the other way around as the metals. So if you increase its temperature, its resistance will decrease, which means that now as the temperature is increasing, the resistance is decreasing. So at the same settings, same voltage, larger current will flow, and also this will change further, probably, I don't know, and then the current will change more. So if you go from low to high in current with the Peltier cooler, so let's say from 2 amperes to 5 amperes, then you have to overshoot the current value, because the Peltier device will cool down, the resistance of it will increase, and therefore the current will drop. But if you go from high to low current, like in this case, we went from 6 amperes and we are aiming for 3 amperes, then the temperature of the cold side will increase, and the total temperature of the system will increase as well. of the Peltier device, then the resistance will decrease. So that means that as we go down in the let's say direction with the current, then this should of course increase, but that will cause the current to increase too. So we have to sort of undershoot the value of the 3 amperes. So let's say 2.96 something, and then once the system reaches the equilibrium, the current will increase. So now I will wait for 5-6 minutes and we will see what happens. So I think enough time passed, so we can read the values, and we see that the temperature increased on the cold side to minus 17.7 degrees. That's still pretty nice because we are at 3 amperes or slightly below 3 amperes, but we still have very low temperature, so I'm impressed. And then the voltage for this value or this kind of setup is 8.21 volts, and you can see now that the let's say warm or hot side temperatures are almost around room temperature now. So 26-27 degrees Celsius, that's pretty much normal. Sorry, this wants to turn off. So what I do now is that I jump down to 2 amperes, so 1 full ampere jump, and we see what is the temperature and what are the other values. So I decrease the voltage again until I reach let's say 1.90 something. So you see that as the temperature is changing, increasing, then the current is also increasing because the resistance is decreasing. So just slightly more. I think I stop here with the settings, and we accept this as 2 amperes. So now the temperature dropped by 50% of the previous value. That's a high change. But now we wait another 5-10 minutes and we come back and read all the values. So it's time for another check, and we are at 2 amperes, 5.87 volts. The cold side, this up here, is minus 9.4 degrees Celsius. Then you can see that both of these thermocouples, the hot side and the outlet temperature, are the same, 26.2 roughly. So that means that it's pretty much room temperature, of course, because now this is like let's say 12 watts, which is very low power. It doesn't really do anything. So yeah, but we can still see that the cold side temperature is quite low, despite the fact that we are only running 2 amperes through the system. So now we have the last step, which is 1 amperes. So I just go down with the voltage, so I bring down the current to something like this, and I will wait a bit and we will see how the temperature changes. But you can see that there is a 10 degrees drop already in the temperature. Now it's more like 12 degrees, and then there was a big relatively big jump in the hot side temperature as well. So we can see that at 1 ampere we are already in the positive region with the cold side. I will let this run for a while and see what happens, how cool this stays. So let's check back in a few minutes. So I think this can be our last measurement for this series. So we can see that the hot side and the outlet temperatures are the same, 25.2 roughly. 3.22 is the voltage, and 1.02 amperes is the current, and the cold side temperature is 3.6 degrees Celsius. Now it's positive, so there is no ice in this area anymore, and the fog disappeared from here. So this is what we got, and this is basically the last measurement for this current versus cold side temperature series for this particular device. And what I will do now is I will determine what is the highest current that we can run to achieve the lowest temperature, so Imax versus Tmin. And with that current setting, I will run the device, and I will put the thermal load on it, which is our well-known other CPU cooler. So I will use this, and I will put this on the top surface of the cold side, and I will put the thermocouple on the side of this cold side, as I did it in the previous two videos for the 06 and 03 coolers. So I will monitor the temperature of the cold side directly by applying a thermal load on it, and we will see what kind of temperature we can reach, and we will see what are the readings of the outlet temperature of the thermal loads, heatsink, and so on and so on. So now we will jump to that part. So we have arrived to the last step of this test series, and just to remind you, this is the TEC12708, so the 8 ampere Peltier cooler, and you can see that these temperatures are the same or very, very close to each other, which means that this is basically the room temperature. So this is our initial temperature. And as you can see here now, I installed the other CPU cooler. Just to remind you, it's basically this guy here. And the thing that is installed is not too different, or I mean, it's the same model. I just removed the plastic frame, this thing, and these two metals, and that is installed on the other side. And as I mentioned in the previous video, this surface that you can see as a gray surface, it is gray because it's covered by the thermal grease, but the surface area or the perimeter of this surface is not exactly 4 by 4 centimeters. It's more close to 3.5 times 3.5, which means that we are not covering the entire area of the cold side of the Peltier cooler. That means that we do not utilize the wall surface, so there is no heat transfer across the wall surface of the cold side. Which is not necessarily bad, because we will do the same with all the coolers, so at least we do this systematically, but we could use the wall surface and then it would be better. If I would have two of these coolers that I have as the cooler of the hot side, then it would be nice because the cooler of the hot side covers the entire surface. But I just ordered one of this, and that's what we have now. So maybe I can show it here. So I removed the plastic. So you see that there is an edge or a difference here. It goes in. So the thermocouple, which is connected to this thermometer, is under this edge. So this edge is basically pushing the end of the thermocouple against the cold side of the Peltier cooler. It's like I try to get some piece of wire. So you see this wire, and then the thermocouple goes under like this. And of course on this surface we have the cold side. So that's how I attach the thermocouple to the cold side. So that's how we will measure. And I might also use an infrared thermometer just to look around and see what is the temperature here and there. But this is not so good because I cannot really have access to the middle of this structure. So everything is clamped down. I spread some thermal grease on the cold side. So we are only waiting for the numbers, and I know the numbers, so I made my math. And the minimum temperature, according to the equations, should be minus 25.29 degrees Celsius. Of course, we can be happy if we reach minus 25. But actually, when we used 5 amperes, we were very close to that. And so this was the Tmin and the Imax. So the current, which is the maximum current that we can efficiently feed to this device, is 5.25 amperes. And if you remember that first I started from 5 amperes and I still saw an increase from 4 to 5 amperes. I saw an increase in performance, so the temperature on the cold side, which you could see here, decreased. But then from 5 to 6 I wanted to go directly, so skipping 5.5, and I already saw that the temperature started to increase on the cold side. So then I decided to measure 5.5 first, and we could see that the equilibrium was somewhere around that area between 5 and 5.5 amperes. And that's what we got basically from the equation. So 5.25, it's right in the middle. And another notice, we now have a different load, or actually we now have a thermal load on the cold side. So probably the values on the multimeters will be somewhat different because now there is a thermal load. So we will see. But what I will do now, this should show 5.25 amperes, and then we will see what are the temperatures and see some other stuff. So first of all, I turn on the coolers and then I turn on the power supply. So hot side cooler is on and cold side cooler is on, and it's just pushing the air very strongly. And now I turn on the power supply, but I turn this on and off because this turns off automatically after 5 minutes, and this was really close to that. So power supply is on and we are at 1.3 amperes, so let's jump to 5.25. And if you remember, we have to overshoot a little bit because of the change in the resistance. So you can see that as the temperature is changing, the current drops down. So if we want to aim for 5.25, we have to set it like 5.30 something. I'd say 32, for example. So as you can see, the temperature of the hot side went up noticeably, and I can feel that there is a warm air coming out, or slightly warm. And then I can feel that quite cold air. Yeah, this is very surprising that on the other side of this fan there is a quite nice cold air coming out. And you can see that the thermometer is showing 13 degrees, 13.7, sorry. But I have to adjust this. Okay. So now it's better. Sometimes the thermocouple is not touching the surface properly, so I have to make sure that there is enough tension in the wire so it is pushed against the surface properly. And now you can see as I moved it a little bit, now it's pushing against the surface properly, and I can measure 8 point something And as you can see, we have the small drop, so I increase the voltage a little bit. So now I'm trying to measure the cold side with the infrared thermometer, but it's just so clumsy because I cannot access that small gap. But this was, for example, from the gap. I hope you can see it. So 17.7 degrees. So that should be like the air which is being pushed towards me. And I can do a test. So keep your eye on this number 33, so the temp 2. So now I remove it. I touch it so I can demonstrate that that is the one that I changed, so 35, because now I'm touching it. So now I push this in between the heat sinks, or the fins of the heat sink of the cooler, and we see what will happen. But you can see the temperature is going down, and this is now below the room temperature, but it's going down very slowly. As you can see, it's like 0.2 degrees per second roughly, but it is going down. But still, as you can see, it's going slowly but surely. So now we are a bit above the desired current, so I change a little bit. I'm just trying to adjust the position of the cold side thermometer. So I think I know what is happening here when I change the wire. It's not only that I increase or decrease the tension between the wire and the surface of the cold side of the Peltier device, but for example, if I move it towards the edge of the, like the physical edge of the Peltier device, so I move it towards the outside, I show it, then of course that is further away from the contact area where the heat sink meets the cold surface, the cold side of the Peltier. And that means that there is less heat transfer there. So now I do that. So I move the wire towards the edge, and with that, the temperature here should decrease. And as you can see, it decreases. So as I move closer, the temperature is increasing because we are closer to the heat load. So it might be so that it's more smarter to measure the outlet temperature in this way, like I do it now. So I just poke in the wire in the middle of this heatsink, and then we see that we are like 22 degrees. But nevertheless, now we can see, and I can feel it on my chest, because this is roughly at the same height as my chest right now. So I can feel that the cold air from this heatsink is coming and cooling down my chest. So I can definitely feel that this is lower temperature than the room temperature by a few degrees. Actually, we can check how much. So I just put this here and let it reach the room temperature. But you can see we were at 22 degrees, plus minus few tenth of degrees, but now it's going to 24. So there was a significant difference. I mean, like 10% difference between the room temperature and the cold air temperature. And what I can also do is that I can put this directly to the heat sink and see what is happening there. Well, not too much. Okay, so that's the heatsink. I explained to you in a few seconds. So now you cannot really see, but I removed this metal plate from this guy here, and therefore those pipes, or the surface, upper surface of those pipes, are revealed. So I can go in with the thermocouple and touch the surface of those, and that is basically showing us the heat transferred from this side of the heatsink to that side of the heatsink, and that's what you can read here. So that is this 18.4 degrees Celsius, and that's what you can see there. So I just put back the cap on the thermal grease side of the heatsink. So I think there is nothing more to say about this, but I can definitely feel a colder air coming out from this kind of heatsink by using this thermoelectric cooler. So I will be really curious about the other guy, the 10 ampere model, because that should be the next which I'm going to investigate. So I still have this, which is the 10 amperes, and then I have the biggest unit, which is the 15 amperes. So this will be really difficult to study. And actually I hope that I will not reach the 10 ampere limit, because with these larger Peltier units it's possible that I have to go about 10 amperes, and then in that case I will lose the possibility of measuring the ampere from here. But now I can see that there is roughly 0.5 amperes difference between the value measured here and the value shown on the power supply. So I just simply apply that rule and go by that. But yeah, we will see. But you can see there is like 2 degrees difference from the room temperature, but I can feel, so it's not necessarily the number, but the way you feel. It's like when you are in a humid air or something like that, you can feel the temperature in a different way. So the observed temperature is different than the measured one. And this happens here. You have some moving air, and then it's slightly colder, so you can feel that breeze. So this was the test of the 8 ampere unit, and the next part will be the 10 ampere unit. So I hope that this video was useful for you and you could learn something from the measurements and from the data, and see you in the next video.